Okay. Okay, so as you can see on the first slide, the laser is coming out from the eyes of this guy. It's kind of CGI, definitely. But it shows that how intense it is. So the intensity is also one of the property of the laser. Okay, so what do you see in the first slide? So properties of the laser, I mean, there are different properties. We are starting from monochromaticity. So it has to be monochromatic. So monochromatic means it has to be like one wavelength, one color. So if the wavelength is one, then it will be one color. So if you see on this right side here, we call spectrum. Okay. And along the x-axis, you see the wavelength, and along y-axis, you see the intensity. Okay. So different colors here, they have a different intensity. So that is why this spectrum is formed. Okay. So I'm starting with this one because I don't know, some of the people, they don't know exactly on the spectrum. And let me see how many people are there now. Salman is here. Okay. Anyway, so, and also if you see here, you know that the white light, it has all the colors. Okay. And so in case of white light, we see this kind of spectrum much broader. In case of red light, different shades of red you can see. Okay, if you use a prism, what prism does actually is disperse the light. So if the light is white light, so it disperses the white light into the different color, because the white light contains all the colors. Okay, if the source is red here, so it's not a white light, so it means it will disperse the red color, but maybe surrounding wavelength of the red colors as well. And if we have a laser, this is about the red color, not a laser, and this one is about the red laser. Okay, so in this case, because ideally there should be only one wavelength. Okay, this is the ideal case. So it will emit, or it will disperse only the red color. Now it has to be one wavelength and one color. So if the wavelength is one, it's obviously there will be a one color. So how we know that the laser is monochromatic? How can we know? So this spectrum actually, it tells us. Okay. If you see here, this is the ideal case, this one. Okay. So you can also read here the degree of monochromaticity of a light source can be specified by giving the line width of the radiation. So line width, it's a simple spectrum. Okay. And here this spectrum is broader, and here this is also actually a spectrum, but ideal case, because it has only one wavelength, so it's like a line. Okay, this is a very extremely ideal case, which is practically, I mean, it's not possible. So first property is monochromatic. Monochromatic mean it should have one wavelength and one color. Okay. So how we can measure? I mean, how we can know how much this laser is monochromatic? So using this formula, we can guess somehow. Okay. If you see here, this is a spectrum as well. Okay. Just drew it to show you the width of the spectrum, like here, is delta F. Here will be also delta F. And the center of the spectrum is F naught. Okay, the center wavelength. So if we divide the width of the spectrum with the center wavelength, we get some ratio. Okay, and it will tell us that how much this laser or the light is monochromatic. So, like if, let's suppose if the bandwidth is like, we can say it's like 10 nanometer. Okay, and the center wavelength, we can say, okay, 532. I cannot write properly here. Anyway, so 10, you divide with the 532, nanometer cancel with each other. So whatever the answer comes, that shows that the monochromaticity of this laser. Okay, so it depends. Usually I took this 10 nanometer, just randomly. Actually, it should not be 10 nanometer in case of a normal laser. Okay, and even less than 1 nanometer. Okay, so this is monochromaticity. One thing you have to keep in mind when we study the ultrafast laser, in case of ultrafast laser, the theory is somehow different in the sense that in case of ultrafast laser, we have broader spectrum. We don't have a line spectrum there. Broader the spectrum, shorter the wavelength. Sorry, shorter the pulse duration. But anyway, that when the time, when we reach to that ultrafast portion, then we see. Okay, so now we move to the next slide here. Second property here is coherence. So what is coherence actually? Waves are supposed to be traveling in a similar direction, similar amplitude, and similar phase. Okay, so this is the example here. And if you see the animated kind of, you can see in case of perfect coherence, the waves are supposed to move like this, which is also, again, extremely ideal case. Now we move further to the coherence. Actually is somehow, sometimes it's difficult to understand in some cases. So I have 3 more slides about coherence. Okay, so what do you see here? There are 2 kinds of coherence, okay, which I mentioned already, I think in the first talk. I don't know, I don't remember which lecture. So temporal coherence and the spatial. So temporal, obvious, is depend on the time. And if you see here the animation here, if there is a perfect temporal coherence, then the case will be like this. Okay, there is no time difference between the waves of the 2 waves. Just for example, I'm showing here the 2 waves. And if there is no temporal coherence, then the case will be here, what you can see. Okay, so the waves from each other temporarily shifting from each other. Okay, and this is very ideal case. This is the normal case somehow. And on the left side, you can also see the similar kind of thing. This is coherent and this is incoherent, and you can see the time difference here, difference between the waves here. Okay, so temporal. This is temporal coherence. Okay. Now we move to the. You can read whatever written. I mean, I just explained in a simple way. Like at one point in space, their phase difference stays the same over the time. Okay, like here, the same. Here is not same. Here is not same. Giving the example of two waves. Okay, let's move to the next slide now. Spatial coherence. Spatial coherence, you can see in the animation as well, but the x-axis is space. And in the previous case, the x-axis was time. Okay. So spatial in the space. So here you can see with respect to space or x-axis, the two waves are shifting from each other. There's no time here in space. Here they are perfectly coherent. Okay. Here as well. And here you can see the shift. Okay, so what is that? At the same moment in time, they keep the same phase difference at different points in space. So here it's not keeping the same phase difference, okay, in this side. So this is spatial coherence, okay, because coherence is always confusing somehow. So that is why I thought some more about the coherence. If you have like different colors here, you can see the different color wavelengths here. And it's red here. This is red. This is here different colors. This is white light. Okay, so this one is white light here. Many different colors. Okay, and this is a one color. So it means it's a monochromatic. Okay, but still it's non-coherent. So even the light is monochromatic. Monochromatic. So it's not necessarily be a coherent. So, and the third portion is a monochromatic as well, but along with monochromaticity, it is coherent as well. Okay, so see the difference. And this difference is animated here. Here, incoherent wave, okay, random, completely random kind of the shifting the phases and everything. Here is partially coherent. It's not animated 100% perfectly, but it's showing this partially coherent means the waves still move somehow, but relative to each other, not so much random. And here is a coherent, fully coherent. So you can see they are moving with a phase, same phase difference. Okay. And so that is why. So first thing, keep it in mind, even though the light is coherent, the light is monochromatic, it is not necessarily via coherent. Okay. So this is how the things, okay. And this yellow portion here, if you see, it's written that coherence length is very important to know in some cases. Coherent time may also be. It will tell you that how good your laser light is. Okay. So coherence length can be from few centimeter to few kilometers. It depends on the quality of the laser. Okay, and that is why the coherence is very important. Okay, so here monochromaticity, coherence, and the line width. Line width we saw in the first slide, kind of spectrum, line spectrum. Are they related with each other? Yes, it does. Okay, it relate to some certain extent. So what you see here in this animation, first thing is monochromaticity. Monochromaticity, as I told you, that one color, one wavelength. Okay, so here this line is, you can see it moves the green wavelength somehow, different shades of the green wavelength. And here this is coherence. Okay, so you can see somehow it's shifting.
Excuse me, sir.
Yes.
सर पॉइंटर अगर आप साथ में दूसरे कलर्स और थोड़ा सा पॉइंटर को मोटा कर दे तो
I
सर
don't
मिक्सअप हो
have
जाता है.
this option actually. I don't have this option. Let me see.
अच्छा.
No, I don't have this option here. Color I can
ओके
change,
ओके
but not the width.
ओके सर.
Yeah. Okay. So what I was saying, that these things are related very much. If the light, first thing, if the light is monochromatic, one thing you need to observe, the spectrum. Okay. So spectrum, if the light is monochromatic, spectrum should not be wide. Okay, wide enough. So it will be like if you see this red portion. Okay, and just a minute, somebody is chatting here.
Excuse me, sir. Sir, you can use the annotate option, which is at the right side of the screen.
Yeah. Wait, just a minute. I think this is Arusa's mess. Okay, you replied already.
Yes.
Okay. That's fine. Okay, so what problem you are facing, Salman? Now tell me about the pointer color or whatever.
Sir, the pointer size is so thin that we mix up things that which diagram you are mentioning and you are sketching the line over there. I think there is on the right side annotate option. So the at annotate option
Right
you
side.
can use there the pen.
No. Right side
you
of
can,
the this PPT file doesn't have a right side any option. It has the options down, but down it doesn't have an option to change the width of the pen.
no, sir. Not on PPT. You can use the WoW screen. Here is option on the right side.
Just a minute. Let's see.
Maybe.
I don't see. I don't see this kind of option. Maybe, later on you can tell me offline or something like that.
Okay, sir. I'm sending you screenshot also.
Yeah. Okay, so what I was saying, first the light is if the light is monochromatic, the spectrum has to be very narrow. Okay, so if the light is not monochromatic, the spectrum will not be narrow. Okay, and after that, coherency. Sometimes it happens that even the light is monochromatic, but it's not coherent. Okay, but it affects the spectrum as well. Spectrum get broader in any case. So coherence, monochromaticity, and the line width, they are interlinked with each other. Let's move to the next slide. Same thing. This is your the line width, okay, and this is also the line width. This is the ideal case, okay. This is the ideal case. This is the finite coherence, finite wavelength. It means ideally we cannot have a line-like spectrum, okay. Ideally spectrum has to be like this. We cannot have so much, I mean, like such a perfect laser, okay. In general, we say that the laser is very much monochromatic and it's coherent, but actually it's not like this. There is always some other wavelength existing. So that is why spectrum gets broader, okay. And this is what is mentioned here, okay. So they can never be perfectly monochromatic and can never be perfectly coherent. So that is why we need to know the coherent length or the coherent time of the lasers. If it is 100% coherent, then we may not need it. So, but it's not 100% coherent. Okay, so now let's move to the next slide. How we can find out the coherence length and the time. Okay, so coherence length and the time, they are interlinked. Like this is coherence length and this is time, and the c is the speed of light. Okay, so if you see on the left side here, it's a coherence length. Okay, so what it's written, you can read that the length up to which the light wave train, okay, light wave train maintain its phase, same phase, okay, and the coherence time, so time up to which the light wave train maintain its phase, okay, maintain its phase. This is how we can calculate the coherent length and how we can calculate the coherent time. So if we combine both these formulas, then we get this one, okay. So L coherent is equal to C and then time coherent. So we can find out the coherence length and coherent time with this formula, time and length. One example. In general, I mean, if you see in the form of a wave, like this. This side actually, it shows that the coherence length phenomena, and here coherence time phenomena. So this color, which is kind of blue color here, this, you can see this wave, okay. So if there is coherence, and we can see like a red one. If there is a long, I mean, coherence length is very long, somehow you can say. But if the coherence length is short or very short or almost no coherence, then you can see this mustard or yellow portion like this, okay, like randomly moving. And here on this side, the green one is a long temporal coherence, and this red one is short or almost no coherence. So if you see the wave like this, then you can guess, okay, this one is coherent and it has a long coherence, and the other portion is randomly moving or something. It has a short coherence or it doesn't have coherence. Okay, so one of the example, I mean, if we take the helium neon laser, okay, a free running CW type general purpose laser, then and we can assume that the frequency, the width, it can be converted into the wavelength. Okay, but here is a frequency. This is if you have a spectrum like this. So this is your frequency, this is your intensity. Okay, so this one is like this portion. Okay, so this is 1.5 into 10 to 9 hertz. This 9 is power actually. It's not, it's a power. Okay, anyway, this 9 is power and it's hertz. Okay, if we know this thing and if we go back these formulas and this one, so we can calculate the coherence time, okay, and the coherent length. So what is the formula in first case? If we have the time, this is t coherence, okay, at 1 over delta nu. Okay, so 1 over delta nu. So if you find out this one, okay, and this will, if you calculate, I mean, I'm calculating here, so it will be like 0.667 nanosecond. Okay, and if you want to find out the coherence length, and the formula is this one here, okay, C over delta nu. So in this case, it will be like 0.0, sorry, 0.20 meter. Okay, so this is the coherence length, this is the coherence time. So if you see the helium neon laser, it's a laser. Okay, and laser mean it's a laser, it has to be monochromatic, it has to be coherent, and it has to be very narrow spectrum, it should have. But if you see here, the coherent time actually is just 0.667 nanosecond. Okay, so after this much time, it get incoherent and then coherent again, incoherent and then coherent again, incoherent and then coherent again. This is how it this thing works. And similarly here, this is a coherence length is a 0.20 meter. So still, I mean, if you see 0.20 meters, 0.2 meters, I mean, it's very small length. So even though helium neon laser is a coherent laser, still you can see that the coherence length is only 0.2 meters. And after this one, it become like incoherent and then coherent again. So this process is repeated. Okay, so this is general purpose helium neon laser, which is used in the labs. Standard, not very high quality, but not very bad quality. Still, it's considered to be a laser. Okay, and its wavelength actually, the center wavelength is 632 nanometers. So frequency can be converted to the wavelength by using this formula. Okay, for your convenience, I mean, if you want to see. Okay, so now we'll move to the next property. This next property actually is directional. So directional, how many people are there? Let me see first. Okay, Nabil is here today. Iqbal. You are here first time? Mohammad Iqbal.
Yes, sir.
It's the first time
Today
here.
is the first.
Ali, which Ali is this?
Sir, it's Ali Isnan.
Where your other name? Okay. Okay,
Sir,
Fatma. It's okay, no problem. Fatma Noor, Tahura, Rusa. Umaima Rizwan, I think she's first time here. Umaima, can you hear me?
Yes, sir.
Umaima, can you hear me? Yeah. So
Yes, sir.
you are first time here.
Yes, this is my first class.
So I mean, how come you decide to come today, the class?
But
Can
actually,
you?
there were connectivity issues
Okay.
last time. That's why.
Okay. So can you please introduce yourself? I mean, because you are first
Yes,
time.
sir.
Yeah.
Yeah, yes, of course. Sir, I did my bachelor's in physics from Islamic University, and then in major physics, and then I did master's from LUMS, again in major physics, and my batch was session was 2020 to 2022. Then I have been teaching in a secondary school as a science teacher. So
Okay.
that's all about my short background.
Okay. So your session lumps actually is 2022,
Yes, sir.
and what is your specialization?
Sir, material science. I did my a master's thesis project on uh, two-dimensional semiconductor materials, where I used Raman spectroscopy
Who was your advisor?
as Dr. Amar Ahmed Khan
Okay. Okay.
from optics physics. Yes, physics optics lab.
Probably 2022. I was there as well. I don't remember if I
Yes,
have seen.
sir. Yes, sir. I think you were there.
Yeah. Okay. Okay. So who is the new here? Muhammad Iqbal, can you please introduce yourself?
Assalamu alaikum. Sir, actually, I am from Sargodha.
Okay.
I have done my BS from Sargodha University and also MS degree from the same university. My specialization was LIPS, laser induced breakdown spectroscopy.
Okay. You
Now
are
I am
okay. Okay. Yes.
sorry.
Continue. Continue.
I am working on some kind of photocatalytic properties of nanoparticles right now to change my field because LIPS is not trending right now in our country, especially.
But why did you decide to take this course?
This because my background is mainly is in LIPS, where laser is main thing in that field, laser induced breakdown spectroscope. So that's why I decided to
But
take
you are
this.
changing your field now, so
For safety purpose, to enhance my knowledge on both fields, because my main knowledge about is LIPS, but right now I'm starting my work on that field. But
if you are inconsistent, then it's not good for your career. It has to be consistent. Changing the field is not good for career.
but trend.
Anyway, I mean, it's okay. It's up to you. I'm just, from my experience, I'm telling you.
Okay,
Okay.
thanks.
So, Umaima Rizwan, how did you decide to, I mean, to take this course? What is like? Umaima?
Yes, sir.
Yeah.
So actually, when I was at LUMS, then I was really motivated by laser spectroscopies. So when I first came encounter with your course like ultrafast laser course, then I really I got interested in that course as well, because I want to join this course. I think it will help me out in the future if I understand this course completely.
Yeah, but this course is not on
So
the, yeah, sure. But this course is mostly based on the ultrafast laser, not on the applications actually. Some
yes,
application can be
but
discussed. Yeah.
it will also benefit me. I also learned a lot from this course. This is my motivation.
Mhm, mhm.
So
Okay.
that's why I decide.
Mhm.
Yep.
Yeah, actually, I also have been offered 2 courses when I was at LUMS, actually, that laser
Okay.
engineering course and photonics. But I don't think you were at that time. I don't remember if you took that course. Yeah, anyway. Okay, so
No, I didn't took those courses. I think I choose principles of optics because my advisor advised me to took this course for that will help me in my research. That's
okay,
why.
okay,
But I remember that you were there. That's why I choose this course.
okay. But I don't remember your name, actually, so probably.
Okay, no problem.
Yeah,
Thank you, sir.
you're welcome. Okay, so the next property is directional. It has to be monochromatic. It has to be coherent, and it has to be directional. Okay, so what is the meaning directional? I mean, if you see the light bulb or white light in general, and you can observe, I mean, you can see here the light is spreading in all the directions. Okay, here as well, light from the bulb spreading here as well. It depends on the kind of the bulb. But anyway, the white light coming from the bulb or any white light source, it spread in all the directions. Okay, so it's not directional. Okay, even though in some cases, if we have like a halogen lamp, a sodium lamp, which are considered to be monochromatic, but they are not coherent. And even in that kind of light sources, you can see the spread of the light is not very much directional. Okay. So one of the important properties is directional, the property of the laser. So here, directional and highly collimated. Highly collimated, it depends on the conditions. Okay. But it has to be directional. If you see this on the right side here, and this animation also, as compared to the light, white light from the bulb, from the laser, you can see the light, it does spread, but not that much. Okay, it does spread, but not that much. So it's a directional. Okay, so it's not like bending in all the directions. So this is one of the thing. Like here, if you see in this diagram here and here, the beam diameter is just exit, I mean, from the laser. It's like this, and after a few maybe meters or something, like it depends on the laser, it's like this. So there is a little spread there, and light is diverging, but it's not like a white light source in case of white light source. Okay, so how we can determine the directionality with the
Excuse me,
naked?
sir. Is there any relationship between directionality and coherency?
uh, yes, definitely it is. You will see more divergence.
Okay, sir.
Okay, so how we can judge, or how we can measure the directionality, or how we can determine the directionality? Okay, it's by divergence. Okay, and laser beam, as compared to white light source, it has the least or much less beam divergence. Okay, and it remains parallel over a longer distance. You can, this kind of experiment you must have seen, or you can do by yourself using a pointer laser or something like this. Okay, So here, this is the example. In this animation, you can see, although there is a spread, laser is diverging by sure, but it's much, much less as compared to the white light. So how much it is directional? For this one, we need to know the, we need some measurements to find out the divergence. Okay, that we will see in the next slide. Okay. The angle of divergence, actually, how much is diverging, how much is going away after leaving the slit of the laser source. So the formula is this one, which is very simple. And if you see in this diagram here up, and this one also shows actually, but it's continue. And this kind of measurement we usually take in the lab to find out the divergence. Okay, so what we do here and here, diameter, okay, and of the beam here and here, and the distance from the source. Okay, so like here, this is a D1 here, it will appear here D1, and this one is D2. Okay, if you see this animation, I hope you see. And what is the distance of D1 and what is the distance of D2? Okay, so X1, X2. So if we know these values, and these values, what we do in the lab, we use the CCD camera for this kind of experiment. CCD camera is cathode coupled device, or any camera you can take, mobile camera even can be used. So with the help of this one, we can know the diameter at two different places and the distance from the source, and we can find out, we can calculate the beam divergence. So that will give you the with the help of this one, you can determine the directionality of the laser. Okay, so this is how you can determine the divergence. Divergence is directly related to the directionality. Okay, this divergence, practically, this is the perfect source. Okay, perfect way, not source actually. Some practically, some people, they do some practical calculations. It can be compared with some experiments here. Beam divergence due to diffraction. Because the beam is coming out from very narrow source, usually we use the slit or very small hole, small aperture. Okay, so when the light passes through from such a narrow kind of hole or aperture, the light diffracts. Okay, and because of this diffraction, we can measure the beam, that divergence. Okay, so the standard formula you can see in any other textbooks. Lambda over d, 1.22 is a constant factor, and it's come from the geometry of the diffraction. Lambda is a wavelength, and the d is diameter of the laser aperture, from where the laser is coming out here somewhere. Okay, and in case of helium neon laser, this is around 10 to minus 3 radian divergence. It's very less. Okay, and or like a general purpose helium neon laser. Okay, and the laser beam increases by about 1 millimeter for every meter it travels. Divergence, it's spreading 1 millimeter. This is about the helium neon laser. Okay, so 1 millimeter for every meter. Okay. So, but it depends on, I mean, if the laser is very good quality laser, the divergence will be much less and the spread will be much less. Okay. After that, we move to the polarization. Polarization, I don't know, I mean, if you people have studied already the optics. Okay, so it's 10 minutes left. Okay. So, you know, the light is electromagnetic. It's a field, electromagnetic field. It has electricity, it has a magnetism as well. Okay, EMP. And if you see here, this yellow portion, it's the orientation of light waves vibration. Simple word. Electric field or magnetic field, these vibrations, okay. If the light is unpolarized, which is a general case, I mean, light is coming from the sun in the daily life or whatever you observe, it's unpolarized. Okay, so unpolarized light has to be like this, you can see. And if it passes through any kind of polarizer or polarizing filter, depends what kind of polarizer. Okay, I'm just telling in general that you people to understand what is polarization. So after passing through, it becomes polarized somehow. It depends whether it's linearly polarized, circularly polarized, or any other, or vertical polarization. Okay, so polarization or polarized light is random. It has random orientation of vibration of electric field and magnetic field. But once it's passed through a polarizing filter, then it becomes polarized here. So laser is already polarized. Okay. And we don't need to put any kind of filter for the laser. So here, the direction in which the light waves electric field vibrates as the laser beam travels forward. Okay, so this is a polarized light. Electric field vibrates in the same direction where the beam is traveling in the forward direction. Okay. Polarization. So, as I told you, there is a vertical polarization, there is horizontal polarization, there is a circular polarization, and these are the common vertical. Sometimes we call linear polarized, or not linear, horizontal polarized. So this thing can be clear here, can be seen here actually. It's not clear here, it can be seen here that this portion, it shows linear polarization. This portion, it shows horizontal polarization. Okay. And did you notice that? What mistake did I make here? Anybody notice?
Yes, sir.
Yeah, what?
Sir, in red section you mentioned it's linear polarization, and
Yeah.
in green section you said
Yes.
it's horizontal. However,
Yes.
both are linear.
Yes, yes. Good. You are listening, it means. Good. Yeah. So the vertical and horizontal polarization is a category of linear polarization. So linear polarization can be vertical and can be horizontal. So this is the field of vibration here in case of horizontal, and this is in case of vertical polarization. Okay. And if we move further, here, this is a polarization representation. Okay. So polarization representation is kind of vector we are showing here. In case of a linear polarization, you can guess It's going up and down in case of a circular polarization. And this linear polarization can be a vertical, can be a horizontal. Okay, this is a circular one, it's circulating around. Unpolarized, it is random. Okay, to understand more, much better way, next slide will also help you. Here, this is your linear polarization. Okay, this one is your circular polarization, circulating. Okay, the field is circulating, and this is unpolarized light. Okay, so in this way, I mean, it's visualized much better way to understand somehow. So linear, circular, unpolarized. So this is just about the polarization, but the laser is already polarized. Okay, and not the circular, but linearly polarized. Okay, after that comes brightness. I have 5 minutes. I think much better to take the questions if you have. So we'll continue rest, I mean, in the next lecture. So if you have a question, please go ahead.
Okay, in this case, in the diffraction of the laser beam is due to the circular aperture of the beginning of the laser.
No. Sorry. Okay, complete your question.
But I have here that some people don't like to talk about diffraction about only for the laser light. It means that to occur diffraction, you need to have an obstacle or that cause that diffraction. But in some case, some people tell that light is also autodifractive. What do you think about it?
Actually, I didn't 100% understand your question. But light diffraction, it depends on the things. I mean, laser is cannot be auto-diffract. Okay, it depends from where it passes. Okay, and this circular polarization, actually, circular polarization, you can polarize this circularly by some means, but the laser itself is not circularly polarized. Laser is linearly polarized always. By some using certain techniques, we can make it circular polarization, but it's not naturally existing polarization state.
Okay,
Sir,
thank you.
same question was coming to my mind that how is it possible? I mean, circular polarization, ever heard for the first time in studies of laser. I mean,
No,
how is it possible?
I'm not saying about the lasers here. Here I'm
Yeah.
telling you that what is polarization.
Yes, sir.
Okay, so
Yes, sir.
because it's one of the property of the laser, so you people need to know what is polarization. That's what I'm trying to tell you. So laser is already
sir.
polarized. That is linearly polarized.
Yes, sir.
But circular polarization can be possible with certain techniques. It's a long story. Okay.
Yes, sir.
Yeah, it's high level research. I mean, we can produce some circular polarization as well with the laser. Okay, so anyone else? Okay, so the new guys, they don't have any question because time finished soon.
Sir, I have a question.
Who is this? Gazanfar?
Yes, sir.
Hmm.
Sir, can you open the first slide where you discuss the
The time will
band
finish. I
gap?
mean, if I open the first one, anyway, I will go.
Okay. Just I
No,
have to ask.
if you people have more questions, I can definitely I can have a meeting again. I mean, after that.
Oh, sir, I have just couple of questions, but
Couple means
two.
which slide you are saying?
Sir, first.
This one?
Sir, next. Yes, sir, this one. Sir, here the monochromity, you can mention the formula delta F over F naught. So it's the ratio must be less than 1
It has to be.
for the
Yeah.
maximum monochromity.
Yes, yes.
Okay. Sir, the other question is where you mentioned the we can measure the divergence